While the slides are ready, since I have been given the charge of chairing this session, I would like to speak a little bit about my research. Okay, those who don't know. So, because I'll be not giving a lecture, a formal lecture here, so a couple of minutes I'll talk, especially taking cue from Professor Rai's lecture. In his lecture, he suggested that there should be many microgrids to support local electrical requirement, right? This is something on which DST has taken an initiative 2 years back. They have started a call in intensification of research on high priority areas. Under that call, I was lucky to receive a major grant about 6 crores along with IIT Bombay. So basically we formed a team. Physics, I am from physics, I work at IIT Durgapur. An energy science professor, Sagar Mitra from IIT Bombay, he is the lead. Then we also got, like Professor Rai has mentioned, electrical engineering is very key component there because the device has to be smart. So we got electrical engineering partners from VNIT Nagpur. So three teams from 3 different institutes. We are currently running a project which is a 5-year project. We have just completed 1.5 years. So hopefully we will be working and we will be getting some success in the near future to develop a microgrid which is mainly powered by solar PV, which will commercially procure. Then it will be supported by the batteries to store the energy. Batteries are sodium ion batteries and sodium ion capacitors, which we at NIT Durgapur and IIT Bombay will be developing. And then that entire system will be optimized. Professor Rai has mentioned optimization is very important topic. So our goal is to the electrical engineers from VNIT Nagpur, they will be integrating the whole things and then optimize it. So this is how we actually aim to develop something as per Professor Rai's suggestion. So with this, I think our presentation is ready. So I will not take any time. So stage is over to Professor Dhar.
Thank you. Thank you. Is it on? Okay, I guess I can freely move now. I hope everybody can hear me. This is so. I started as a physics student, but then I realized that science, whether sustainability or anything, is no good if does not do good thing for human being and the mankind and the ecosystem and the world, etc. But that means you really need to infuse engineering with science, as the previous speaker also talked about. But now there is a bigger thing. There is yet a bigger thing, and that is who will execute this science and engineering. In order to execute this, you really need to train students. And in countries like US, the STEM education and all the engineering, etc., has been suffering from the point of view of competition from law, economics, and other areas. So there is a big movement in order to educate students, particularly in the way the industry would like to do. And that's what we call workforce development. So I will discuss some of these things and some of the programs, how we are doing. And at the end, I'll give you some of the examples of research. Of course, I would love to talk about all the defense technologies that I have developed, but of course, I can't talk all of those things in this forum. So next slide. So I am from Virginia Commonwealth University, but prior to being a professor at the university where I am there for about 2.5 years, I was in the Department of Defense for 33, including working at DARPA. So when I joined VCU, I was very interested in looking at the future. As you say, sustainability. Sustainability is a factor of that is also the workforce. Who is going to continue our work? And that is where I am really focusing on. And so what we are trying to do, an integrated work for STEM education, and I will discuss how we are doing it and describe various projects and programs that we are implementing. This is our clean room facility. Here is a Senator Tim Kaine. This is the Nsesd director, and that's our director, our president of the university. Next slide. So if you look at the technology today, the intersection of network, sensors, embedded computing is driving a new era of cyber physical systems. Everything is becoming cyber physical systems. The other thing is artificial intelligence. It is becoming a force multiplier. You know, as you see, AI, ML is in everything, every technology. And finally, system on a chip, neuromorphic, AI, ML, as I said, advanced optoelectronics, etc., are really creating new opportunities. But what is this opportunity? As we are talking, this is a natural science audience, but the next within this ecosystem is engineering. In the engineering product development, industry is interested in the product development. So what we are focusing on, taking the science and figuring out how we can apply to actually develop components and products. As you can see, the intersection of all of this creates a whole variety of applications of technology. So if you go to the next slide, so as I've talked about STEM education, if you go to any industry, government organization, even many universities, they are all vertical. So they all have their innovation platform, they all have their STEM education, and they all do their own silos. What we are doing, this IDISLA program that I've started, is really breaks the silo. So that means it's no more vertical, it's actually looking at horizontal to connect all the silos. So this is the idea I am implementing within the university and within our ecosystem. So if you go to the next slide, so one of the key, very important thing is that physics, engineering, all that, the STEM education alone is not important. It's not, I mean, it is important, but there are many more things that you need to do, such as humanities, arts, etc. So this saying is actually a famous saying in 2011, the guru of the apple. So if you look at it, how do you develop a workforce? It has to be a very holistic workforce where you have to have science, engineering, etc., but also other topics, humanities, arts, etc. And if you look at today's modern way of developing science workforce, you will find that you have to cultivate human capability. Today's, at least in the US, all the students that we are developing are very, very smart, but they lack many other skills. They lack the skills in what we call human capability. You need to develop that as well to build a good STEM education program. So we have to also, I need to go a little further. Also in our programs, it's a project-based learning. And I would give those examples. And finally, experiential learning in an integrated R&D environment. We have many research programs. Currently, I am doing 25 different major research projects. And of course, you have to integrate this. And I'll show you how I'm doing it. If you go to the next slide, you will see I'm going to give you our approach and analogy using a system on a chip. A system on a chip has many layers, and similarly, we have many programmatic layers that is integrated vertically together to develop students for future education, future workforce, and etc. etc. So first thing is to build a program with three core capabilities. Okay, which are the three core capabilities of the system on a chip. One is the IDISPLA, and I'll explain all this. IDISPLA is a digital innovation platform. And then we have the Virginia Microelectronics Center, which is actually a clean room facility. We have two clean rooms, one for materials development, materials growth, such as molecular beam epitaxy, etc., and one to do MOSFETs and device fabrication. And then we have what NCC is the nano material characterization, which is basically looking from nano to meso, atoms to micro size. And finally, we have integrated VIP program, which is called vertically integrated program, where the students from all the way from undergraduate to seniors get involved in a project-based uh, ideas that they are interested. While they're taking their courses, they actually have hands-on work throughout the 4 years. And then finally, we build a strategic partnership. So we actually have many industry partners and many government partners. And then finally, build the ecosystem that I'll show you. So if we go to the next slide. So first is the VIP. So VIP is very important. And why am I talking about this? I have been talking this to many universities that if they find this interesting, they should implement. A VIP is where you have a freshman, to all the way to senior, they come in and they pick a project. For example, this project as a UAV development. So they work UAV development all the way, all 4 years on top of what they are doing. So that's integrated. I have an integrated project where intelligent imaging is my area. So next slide. So as I said, I've given an analogy of a system on a chip, so an integrated chip. So first layer I called it Innovative Discovery Science Platform, IDISPLA, which is really an ecosystem builder. It allows to integrate industry, government, other universities in a digital platform. And then the next, and that gives you an ecosystem. And then we have BMC, NCC that are going through a little bit more description. And then we have the specialized workforce development. Then we have some state-funded, these are large programs, state-funded program over here. And then finally, I talk about the some research. So if you go to the next slide. So the first is the iDisplay. iDisplay was created to bridge the gap. A lot of universities, even industry, they develop STEM workforce, but the problem is in the university, students learn and understand and become a good engineer, but they have this gap between industry and university. And this platform was to actually bridge that gap. That was the idea. But through this platform, we have done many things. Like we will do a seed project and see if that pans out to something useful and then grow that project. Or we do crowdsourcing. We do various type of, I have to go closer. We create various type of communities all the way from, historically bad black colleges to minority institutes to some advanced other areas, communities that can be brought in together in that. And we do projects on that, state-funded projects. So it really is an ecosystem builder. You see how that works. If you go to the next slide, so that's the next layer, which is the Virginia Microelectronics Center. And this actually is an important place where we can actually do the research and training. So we can build devices. If you have a MOSFET, we do laser designs, we do a whole variety of infrared detector development, we do electronic circuit chip, etc. And then we actually partner with a lot of different industry A lot of government entities which use trade-off, for example, cooperative research and development agreement. And if you look on this side, there is a big program by U.S. Congress called the CHIPS and Science Act. Similarly, the state of Virginia has also passed a CHIPS and Science Virginia Alliance for Semiconductor Technology. So this clean room, we are a core component of 5 within the Commonwealth of Virginia. And so therefore, students start learning how to use a TEM, how to use an SEM, how to use lithography, and so on and so forth, right from the freshman years and all the way. And then, of course, PhDs and masters, they all, of course, learn and develop, do those things for their research. So that's an important layer. Next. This is the NCC, another layer. These layers are really capability and can produce the core. They, they, they produce the core capability for the education and training. You can see this has many tools. Of course, BMC and NCC provide state-of-the-art facilities for characterization, for fabrication, etc. So they are the key laboratories at that place. If you go to the next slide, these are some specialized, and everything will come together later. You will see this is a program called Aspire. Aspire is funded by the U.S. Army, which involves 12 universities. It is absolutely developed to train the students, and these are undergraduate senior students, to learn about technology that Army cares about. So it's a very specialized workforce. If you go to the next slide, similarly, we have A-STAR. A-STAR is a program that is funded by U.S. Air Force, and that is really similar. It's a complementary program, and it is involved with 50 different universities within the U.S. to develop students to learn technologies that Air Force cares about. Next slide. This is the veterans program that we are developing, where our goal here is to really, of course, create a certificate, and I'll talk about the certificate in 4 different areas, which is infrared, electro-optics and infrared, radio frequency and communication, edge technologies, and modeling and simulation that I will show you later. But this program is important because this is very specialized for defense. So because defense requires US citizens, we have many international students, very, very smart students, but they cannot go to defense. So we are creating very special workforce development using the veterans from US. Next. So the next layer, if you remember that system on a chip, this is the next layer on top where we have the Commonwealth Cyber Initiative. Commonwealth Cyber Initiative is really a program through the Commonwealth of Virginia, and it really develops technology in cyber security, AI, ML, and all kinds of technology, and it has different nodes. We are the central node, and if you look at over here, these are the primary thrust areas within this, and all students are working on. R&D in sensor technology for smart cities and smart health. So it's all about sensor. Cyber physical systems are all about cyber and sensor and cloud computing, etc. And so these 2 main areas are where you learn all about control, automation, you have sensors, you have instruments, you have monitoring, HMI, human-machine interface, etc. All that comes together in a cyber physical system. So that's this program, and this program is about $8-9 million every year. So if you go next slide, the next level, okay, this is an important slide because within this cyber physical system research, we actually have a miniaturized city. This is a small city within a room, a big room, of course, where there are buildings, there are fire stations, there are hospitals. So these are modular. So I can interchange buildings, or I can make something here in such a way that it's a specialized in particular city where I have miniature cars, small UAVs, small helicopter, all that goes in this room and we can test it. And but it's designed in such a way that you can scale it to the real size. So that's called the open cyber system. Next slide. So this is the, I would say, a small CHIPS Act program within the state of Virginia. And this is, if you look at this, over here is the Senator Warner, this is the governor of Virginia, Governor Youngkin, Glenn Youngkin. And this is a program where we want to do research and development within the semiconductor technology. So there are the entire nodes. We are one of the nodes, and there are 5 different nodes. Virginia Tech is another one, UVA is another one, George Mason, etc. And what this do is collectively all this node creates semiconductor facility like we have BMC and NCC that I just discussed, and other universities have other specialized laboratories that integrates together to actually serve the Commonwealth of Virginia. Many industry partners use our facility. Many other universities use our facilities. I mean, of course, each slide I'm talking about, I could speak a lot more, all the research and all, but I'm just trying to capture the whole integrated strategy, how we are doing it. So if you go to the next slide. So now what I have shown you, the system on a chip, and residing on top is a big program that we just started called Convergence Lab. Convergence Lab initiative is actually a 5-pillar, science pillars, which are shown here. It has quantum photonics, then it has microelectronics, artificial intelligence and neuromorphic, biomedical, and arts. So these 5 pillars drive 4 different technologies. One, and then I'll talk about in a minute. But before that, of course, we have the, remember I talked about VIP and then all these integrated programs and undergraduate, graduate, master's, and PhD, and the workforce development, they all come together in order to drive technology. So I started out, if you have science, natural science, but you have to have engineering to mold the science into something useful, and then you have to drive and execute that and sustain it. So you have to have people, and then when these people learn and become experts and mature, they develop this technology product that's pushed to the industry, and the humankind benefit from that. That's the whole ecosystem cycle. So if you go to the next chart, so these are the 4 areas. One is the modeling and simulation, in which we are building an integrated ecosystem in modeling. Modeling using quantum modeling, semiconductor modeling, device modeling, all kinds of modeling. And then the next area is electro-optics and infrared, which is my expertise, in which building new type of detect technology, imaging technology, and I'll give you an example. And then the next chart. Then we have radio frequency and communication. In here, a lot of radio frequency that are really sensitive area we are working on. And we are working on future G communication, like 5G plus, 6G, 7G. We have infrared optical communication technology, a whole bunch of research that are going over here. And finally, the edge technology and security. What is edge technologies? Edge technologies are those technologies, computing technologies, that uses very little power. It does not use cloud server. So say, for example, you want to have a hardware matrix multiplier on the edge where you have no access to computing, you have no access to cloud, you have no access, you don't have a lot of power. You want to build a technology that does matrix multiplication in the hardware, then you design that chip. Similarly, many other technologies that are worked at the edge. This is really important for defense because soldiers are at the edge where they don't have the capability or large computers. They can just, then they have to be able to process with this low power, low cost technology. That's what this is doing. If you go to the next chart, So that pulls together the whole ecosystem. These are the five different pillars. I talked about quantum, etc. Then they have embedded within them education, integrated R&D, partnership, workforce, etc. And the ecosystem includes all the way from high school to other universities, different institutes, government laboratories, industry, of course, and FFRDC, which are federally funded research centers, and the whole thing are actually, we have within this ecosystem some 55 different organizations. And of course, coupled with all these different other things. So if you go to the next chart, I'm almost done. So I'm going to give you, of course, what I have given you is really an idea. It's not really a concept, but it's a concept that has been experimented in how we integrate research, technology, engineering, everything, and students to become competent scientists and engineers for the future. We are actually bridging the gap between us and industry. We are trying to educate our students, not just science and technology and engineering, but also arts, but also understand the human capability. See, an engineer is actually an economic guy because he has to develop a product. That product has to sell. So all the physics behind it may not be much helpful unless you can sell that product. So it is the whole chain that you have to have. So all student has to learn those things. So if you go to the next chart, so I'm just giving you a flavor of research, okay, in the area that I am working on. So if you look at this chart, if you look on this side, the y-axis is the imaging system. In this particular case, it's infrared imaging system. The y-axis capability, x-axis is computing complexity. So the more capability you get, just like your human brain, visual cortex and retina and eye, the more computation you need, more complexity it gets, and therefore its size, weight, power, bandwidth, everything increases. So given infinite amount of money, infinite amount of bandwidth, you can do pretty much anything, but that's not reality, right? So this is a trade trick. What we want to do is to be able to put a visual cortex on the chip on an imaging system. That's the goal. That's the research path. So if you go to the next. So for example, in the infrared research area, we are doing near term, mid term, long term. And long term is that an imaging system with brain on the chip. Now that's the idea. But we are progressing, learning, we are doing modeling, etc. If you go to the next chart, that will, so this is a concept. When I was at DARPA, I had to develop new ideas that are not just idea on the paper, but an idea that actually gets used by military or even commercial. Here, what we are trying to do research is if you look at a photon coming from the scene, a photon carries many information. For example, it carries brightness, it carries space X, Y, Z, it carries wavelength, what wavelength it has, it carries a whole bunch of things. So this is called plenoptics function. But what we typically do is only harness the brightness. And that's because the prismatic, the way the camera system is designed and developed, then we are stuck with that. But in this program, in this research, we are trying to make the camera more intelligent and try to harness all the information a photon carries. So that's an example. If you go to the next chart, another area we are doing is fusion. It's an example of fusion. It's a visible camera. It's looking at a scene. And you can see that there is a car, there are some lights, that's about it. If you go to the next chart, you see this is a shortwave infrared camera. Same scene. Now you see different things. You actually see this person inside the car, you see this car, And as you can see, if you go to the next slide, so these are supposed to be videos. I don't know why they're not running. If you click on it, no, go back. So anyway, your computer is not running the video. That's okay. You have to back up. Back up. Okay. That's fine.
This one, sir?
It still can illustrate. If you go back up one slide and go into display mode, so you can go into display mode, click right there. See that bucket? Just click that bucket right there. Yeah. Okay. So first you saw a visible image of the same scene. Now you see a shortwave infrared. Shortwave infrared is about 0.9 micrometer to 1.7 micrometer. So it's in infrared. And you see some features. If you go to the next slide, I mean, of course, video illustrates much better. All of a sudden, this is long wave. This is 8 to 12 micrometers, like a microbolometer, or in this particular case, it actually happens to be a microbolometer. So this is wavelength of 8 to 12. And you can see various things. Now you see there's a person you couldn't see before. Other thing you can see is this car is hot. That means with the visible, you can't tell if the car was running or not. Now you know that either the car is running or it was running not too long ago. So the engines will be hot. So you get all this. And then if you do the data fusion very intelligently, this is a very simple fusion in this case, but you want to use artificial intelligence and machine learning to understand how the fusion may be better. If you go to the next slide, you'll see this is the fused image. Now you can see everything. You can see the person, you can see this person, you can see the car, you can also see its engine being hot, and so on and so forth. So this illustrates, you can see much better in video form, but this illustrates that when you do data fusion, you can get a lot more information than you would otherwise. For example, we are working on fusing millimeter wave, radio wave with infrared. That's a very, very challenging problem. Next slide. So, essentially, in summary, what I'm trying to show that while we are doing research, we are bringing in our undergraduate students. Of course, our graduate and PhD students are involved intimately in the research, but we are bringing them and educating and training them in an integrated fashion, working with the industry, so they are ready the day they are graduate and they go. And we are doing this, an analogy of integrated system. An integrated smart chip has many layers that function in synergistically with each other. So that's what we are doing, building capability and so on and so forth, and then finally building this convergence lab right on top of it. So that we have research, we have a whole bunch of research going on, we have education, we have training, and we have workforce for the future. Thank you.
Thank you, Professor Dhar, for keeping time and for such a wonderful lecture where mostly what we have learned is system integration, because normally in research talks, often we only present development of one topic or one device, one small device, but what Professor Dhar has shown us is how different components are put together to perform an objective.
Correct.
Essentially, that is what I have found. So we can take some questions, quick questions. No questions? Well, then I have a question, right? Okay. So it's very interesting, especially I think your main expertise is perhaps the detectors, right? Is it? I'm not sure, but maybe you can correct me. Infrared detectors, yes. So the two images that you have shown at the end, there was significant difference just because of the choice of the infrared wavelength.
Yes.
So can you explain a bit more about the mechanism, why the wavelength, how the wavelength actually makes such a big difference?
Okay, so first of all, you have the UV visible,
Ah.
then you start infrared. Infrared has many bands.
Yes.
What I have shown is the shortwave band and long wave band, right? Shortwave band, by the name, its wavelength is short.
Yeah.
Long wave band is longer
Yes.
wavelength, correct?
Ah.
And it also signifies the temperature here.
Ah.
Because long wave is as the temperature
Less
decreases,
energetic.
right? Less energetic.
Yeah.
So you can see more, you can see people better. So
Ah.
the difference is coming because their characteristics. So short wave can be transmitted through glass, long wave cannot.
Cannot.
So you can see the people. And the whole other thing, like people that were hiding behind,
Mhm.
in long wave you can see them because their temperature is just right. In
Right.
short wave you can't. And so on and so forth. So there are many, many properties there. And you can use artificial intelligence to really make them much, much more intelligent.
Yes. Thank you. Thank you. Yeah. So I think we'll move to the next lecture. Before that, there is a short felicitation to you from the organizers, a small memento to be given to you. Yeah. Thank you, sir. So without any further delay, I would like to invite